Hi everyone, and welcome to part one of a two-part video where I will be going over the input data that's needed to run a linear time history analysis using time diagrams. The add-on module we'll be using is RF-DYNAM Pro, and more specifically natural vibrations and forced vibrations. The vibrations being simulated are usually produced by rotating, oscillating, or pushing machines. So in this video, I'll be going through an example model based on machine-induced vibrations. So with that said, let's dive into this model. So first thing you will see is I have a simple steel frame structure open here. And this is what we are going to be placing our oscillating machine on. And we will be adding in the horizontal and vertical force load cases as well. So now I just want to show you the machine load. Right now we have the dead load open, but if I go to the machine load, you can see where the machine is placed within these openings here. And this is basically just a static force. So now what we need to do is add in the radial forces. So we need to go up here and create a new load case. The new load case dialog box will pop up, and this first radial force will be our radial forces in the vertical direction. And then we just need to create a copy of this and have a load case specifically for our radial forces in the horizontal direction. So we'll click OK. Now what we can do is we can create our vertical radial forces. So what we need to do is go up to new member load. And then we can create our new member load, and this is going to be a force uniform and in the Z direction. And then we're going to enter a magnitude of 0.05 kip per feet. Click OK. And now we can just add in the forces along the perimeter of this opening where our machine is located. And now all we need to do is do the same thing for our horizontal forces. So we'll go to the horizontal load case and create a new member load. And instead of being in the vertical direction, this is going to be in the X direction. And where this is going to be the same magnitude, so 0.05 kip per feet. And so now we just need to add in this load. And we can do the same thing for our opening down in the bottom here. And now we have both of our horizontal forces and our vertical forces. So now that we have our forces for our machine, so we can go into our project navigator on the left-hand side here and go down to add-on modules, and then we can double-click on RF-DYNAM Pro Dynamic Analysis. So now the first thing we want to do once we have the RF-DYNAM Pro add-on module open is we want to activate natural vibrations and our mask combinations. I recommend going back and watching the tutorial videos on the natural vibrations, and these videos I will link below, and these just explain how to enter the input data and run results for natural vibrations. So a lot of this will make more sense, and I'm just going to briefly go over it now. So under mask cases, we want to create two mask cases, one for our machine load and one for our dead load. So we'll just make this first mask case our dead load. And since we're already taking self-weight into account in RFM, we're going to turn off self-weight. And then we're going to check off the option to take the force components from our LC1, our dead load case. And so now all we need to do is just make another mask case, and this one will be for the machine. And we're going to uncheck from self-weight structure and from force components, and then we're going to choose our load case machine. Now under mask combinations, we just want to combine both of our dead mask case and our machine mask case over. So we can highlight both of these, move them over, and then we can just name this mask case 1 and leave it blank. Next, under our natural vibrations case tab here, we want to, under our general tab, and we want to tell the program to run 10 eigenmodes. And then we can leave our scaling of mode shapes equation the same here. Then under calculation parameters, we want to choose the acting masses from our mask combination. And then we are going to keep all three directions activated. And then we just want to keep our diagonal matrix and translational degrees of freedom. We'll keep the method for solving our eigenvalues as default as the line coast solver. And then we don't want to take any stiffness modifications into consideration. So now what we need to do is hit OK and calculate. And now back in RFEM, we can take a look at our results. So we want to go into table 5 and take a look at our effective modal mass factors and scroll down. And you can see that we have our total mass participation of 99% in the y direction and 69% in the x direction and 31% in the z direction. Now it's not necessary to get 90% mass participation in each direction, so we don't really need to worry about that. We do need to find the modes with the greatest results in the x direction and the z direction because these are the directions of our loading. So if we go into the x column here, you can see that mode 7 is one of our most important mode shapes, and then in the z column you can see that mode 10 is our other most important mode shape. And now we want to take a look at our natural frequencies as well. So we can see what our maximum natural frequency is in mode 10 is 37 radians per second about. And now we can go back into the RF-DYNAM Pro module and activate our response spectrum analysis or linear time history analysis module, forced vibrations, and then we would just want to activate our time diagrams. So once I do that, you'll see a couple tabs will appear, and in the time diagram tab, you will see a couple options listed here. So our options are either transient, periodic, or function. So transient is only for a linear time diagram, and so you have to enter your time steps manually, so in seconds and then the multiplier. And you can import and export this from Excel. Then periodic this is the option we'll be using for today. And then a function, as you may guess, is you can enter a function and you can have it calculate your time steps for you based on the function and the step size you choose along with the maximum time. So like I said, we're going to be using periodic, and under this option we want to enter our angular frequency of the machine. And for this example today, we're going to assume that our machine runs at 5.34 hertz or 33.51 radians per second. For the shift, we're going to keep this as 0. And then for the multiplier, we're going to keep this as 1. And then once I hit enter, you'll see that the program creates a sine function with the angular frequencies based on the angular frequency entered. And for this time diagram, this is going to be our vertical component. And so at time 0, it's going to have 0 impact, or there will be 0 forces. And then at time 0.046 seconds, we will have an impact or full force of our loading, so 1. And so this will keep going based on this sine curve. So now we have to enter the time diagram that's similar but not the same, so we want to make one copy of this. And this time diagram is going to be for our horizontal components. We'll keep it as periodic, and then all we need to do is shift this time diagram by a value of half of pi, so this equals 1.5708. If I hit enter, now you'll see that our time diagram has shifted. And now at time 0, we have full force of a multiplier of 1. And then at time 40.047 seconds, we have no force at all. And so this is how we're going to simulate the radial forces from our machine that's oscillating and with our two vertical and horizontal components here. So now what we have to do is combine our time diagram with the loads. So we need to go to our dynamic load cases tab, and you can see we only have the time history analysis of time diagrams activated here because this was the only module that we activated under our general tab is time diagrams. So everything else will be grayed out. And then we're going to be using the linear implicit numeric analysis, and this is recommended in most cases because it provides more precise and better results in most cases, whereas the linear model analysis only uses, this should only really be used for small structures like a cantilever, for example. So then under the next tab, time history analysis, here we have to combine the load cases with the time diagram. So for our first load case here, we're going to choose our radial forces, our vertical radial forces, and then we're going to match that up with our vertical time diagram. And then for the second load case, we're going to choose radial forces horizontal, and we're going to match that up with our horizontal time diagram. When it comes to time steps and maximum time, this we want to change to something smaller from 0.1 seconds to something like 0.01 seconds. And you want to think of this kind of like FE mesh because you'll see later how this can affect the accuracy of your results. So, and then the next thing we want to enter is our maximum time, and we'll enter 15 seconds for this. You can then use the to generate settings over here to generate load cases and result combinations. We don't need this right now, but if you wanted to see the results later and combine them with other static loads so you can do some design work, you can do that here. And this is just something that is handy for if you wanted to mix static loads with the loads generated from this time diagram. The next tab we want to go into is our calculation parameters. And so here we want to do the same input process just like our natural vibrations analysis. This is because the linear implicit numeric analysis does not use our natural vibrations case 1 that we created. And you can see if I go back to general that this is grayed out, this option to choose it. But if we chose the linear modal analysis, we could choose this from here. So what we need to do under calculation parameters is we need to basically just set the same parameters as we did for our natural vibrations case 1. And so we can choose our mass combination and we can choose in all directions. And then our type of mass matrix will just be in the translational degrees of freedom. Then when it comes to the condition, we're not going to use any conditions. Then the last tab we need to go through is damping. So this is the last major settings that we need to look at. And what we need to do here is just enter our damping coefficients for Rayleigh damping. We can't use Leer's damping for our numeric analysis. And so what we can do is go into this tool here that converts Leer's damping into Raleigh's damping. And this is the reason why we ran our natural vibrations analysis, because we needed to find the dominant mode shapes and take the natural frequencies from these. So we can click on this small tool here and we can enter our frequencies from the most important mode shapes, which were 7 and 10. So 7 was for the X direction and that was 33.67 radians per second. And then since we're using a steel structure, we'll just assume that for steel, the dampening coefficient is going to be 0.02 or 2%. And then our other mode shape was in the Z direction, and that was mode shape 10. And we had a frequency of 37.02 radians per second. And then again, we're just going to enter 0.02 and for our damping coefficient. So now we can click OK, and you can see that our coefficients, alpha and beta for Raleigh's damping, were calculated automatically. And then you'll see the function will appear down below, and those dominant frequencies we entered that are damped by a factor of 2%. So now basically that was the last pieces of data that we needed to enter to complete the input data for our linear time history analysis. So now all we need to do is hit OK and calculate. And then we will see the results. And this is the end of part 1. So if you would like to see how to go through the results and everything, I recommend checking out part 2. I will try to link that down below in the description, and I thank you for watching.